offset function. It's not really a function, right? It doesn't have an arrow in the type. I would call it an action. It's like a little imperative program that Haskell's going to execute when we compile and run this one. You can also write it in GHCI. Like in GHCI actually has a special case. If you give it something that's just like, an int, it'll just evaluate it and print out the int. If you actually give it something of type IO or whatever, it'll execute it and, just show you the result. It's actually a special case that has built in, because otherwise, if it just like evaluated it, it would just be like, it's like if I give you a recipe card, like, I'm like, will you please evaluate this? You're like, yep, here it is. It's a recipe card. Like, it's done. But I'm like, no, execute it. Like, oh, okay. Like the default instrument. So GHCI can actually do both. But in general, right, when you actually compile a Haskell application, which we haven't really done, you have to have a module called main with an IO action called main, and when it compiles it, it will do whatever. Like the compiled program will do whatever main says to do. And obviously, you can import whatever you want, and you can call it a function and do whatever. But ultimately, just like Java will run the main method in your whatever the class is. All right, so we have two operators now that we can use to combine IO actions, right? So there's this operator that works on any implicative that says basically do the first one, but throw away the result, and then do the second one. And often, if you're doing IO stuff, that's what we want, because the result actually is not interesting. What's interesting is what it does when you execute it. It might print something on the screen or whatever. And so we can just have a big chain of them, like this. But then we also have this bind operator that says, I don't know if you can see that. Well, yeah, you can see here, it's actually more general than just on IO, right? But I think we have to type down here, just to remind ourselves. There. Right, instead of giving it just an IOA and an IOB, we give it an IOA, but then we give it a function that says, I will take whatever the result is of the first one and then compute or decide what IOB things are running. And we can use that to let this, whatever comes next, because of course this thing could be a complicated thing itself composed of many IO actions composed together. But we can use it to let whatever comes next depend on the output of the first one. And so, right, for example, we said, all right, we're going to do getLine. That returns a string. And then we want to use that string to determine what to do next. So we can make a function. The function is lambda name arrow all of this stuff, like everything that comes after it. Right? We've just written it on separate lines, like just to kind of help us read it. But we could, if we want, we could put parentheses like this just to emphasize that. But we don't need the parentheses because whenever you write a lambda, the body of the lambda just goes as far as it possibly can. And we actually use name here. Right? We don't have to use name. We can ignore it if we don't need it. But if we're going to ignore it, then we might as well just use this operator, which is basically this operator is basically like doing bind and then ignoring the parameter of the lambda. That's actually what it is. And then we also user enters a number and we read it, get our number, and it's done. Incidentally, the reason I had to put this type annotation here on n is because if I left it out, well actually let's see what error we get. We're going to get an error if you leave it out. Ambiguous type variable, A0. It's a little bit confusing, but it says probable fix use a type annotation to specify what A0 should be. That's exactly what we have to do. Let me see if I can explain why it's ambiguous. This is kind of a tangent, but it's interesting. Right, print. What's the type of print? Print says you can give me anything you want as long as I can turn it into a string. Give me whatever you want, I will turn it into a string and then print it out on the screen. Okay? So So that's useful. You can say print 3, you can say print string, you can say print, whatever. Readline says, oh yeah, I will execute, something that's going to prompt the user, or like wait for the user to type something, and then I'll give you back any type you want, as long as it's an instance of read, which tells me how to convert from a string to that thing. Okay. So when we use readline and then immediately do print, right? Readline can return any type, and print can take any type. So put them together, and it's like, geez, like you started with a string and you ended with a string, but I don't know what type you want in the middle, and it makes a difference, right? So GHC basically has no way to figure out. Usually when we use a polymorphic function, if we use it on some particular type, it'll just figure out, oh, you called this with an int as an argument, therefore you must want this type A to be int. But here, it's like the A from print meets the A from readline, and it has no way to figure out what A is supposed to be. And it needs to know, because that determines how print and readline will behave, right? If you choose int, well then it'll only let you type in an int, and it'll print it out. And it'll do an error on anything. Anyway, so that's why I needed to somewhere put any kind of type annotation anywhere. It's like, oh, n is an int? Okay, that means print takes an int. That means readline needs to be returning an int, so therefore I can now figure out what it means. Anyway, that's just a tangent. But that often comes up specifically when you're like reading stuff and then printing it out. But it can come up in other cases too. I guess the other interesting thing I will say is that kind of the reason this is possible, or that this is a thing in Haskell, and it's not a thing in, say, Java, because in Haskell, type classes can be polymorphic in the output. So you can actually have a function that says, I'll return anything as long as it's in this type class. In Java, you cannot have an interface where the output type kind of is the interface type. It won't let you do that. Which kind of makes things easier for Java, but some cool things you can do having polymorphic outputs. Cool. Okay. So this looks better than we had before, right? We don't have a ton of parentheses, and it's kind of like there's kind of one thing happening on each line, right? And this really kind of looks a lot like, it's starting to look a lot like, some kind of imperative program, right? It's like each line is some kind of statement saying to do something. Some of them, return a variable, and we're like using a lambda to do that. So basically, Haskell has a special notation exactly for this kind of scenario. Okay, so I'm going to comment this out, and then we're going to change. We can use something called do notation. Which was syntax sugar. Okay, syntax sugar means it's not really a new language feature, it just gives you nicer syntax for the same thing. And when Haskell reads in the program, one of the first things it does is like translates that nicer syntax into the more fundamental syntax, and then it continues processing it. But it just gives us something nice as programmers. So in particular, here's what we can do. We say the word do, and we have to indent a little bit. I'm not going to indent everything. And now, we don't need, so this operator, if you just have like consecutive lines in a do, it just means to combine them with that operator. So I don't have to put an operator there at all. I just say line, 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 and it'll just automatically chain them all together with this and then operator. Okay, but what do we do with bind? So I'll take these out. Okay, the bind we can do this way. So you kind of switch the order, oops. And instead of writing getLine bind lambda name, you write getLine on the right and the left arrow and then name. So it kind of is supposed to look like, we're taking the output of getLine and assigning it to the variable name, which is really what this is doing, right? And then just like you would expect, like here we have a lambda, So name was going to be in scope for the rest of the lambda, which is all of this stuff. And of course, here the same thing is true. When you have a do block, when I have some syntax like this, name is going to be, I can use it anywhere in the rest of the do block. And I'll do the same thing here. So instead of having bind lambda n, I'll just put left arrow n on the left side. That's it. So this, right, again, this literally means this. So if you're ever confused about what do notation, if you're using do notation and you don't remember what it means, it just means this. So fundamentally, you need to understand like what this bind thing does, and what this kind of operator does. And it just translates it very simply, right? Every time it just sees consecutive lines, it sticks this operator in there, and every time it sees a left arrow thing, it does, this thing, bind, lambda, whatever, and then the rest. But it lets us write some things in this nice format. So this is not specific to I/O any more than applicative is specific to I/O, right? There's lots of things that are applicative. Things that support this bind operator are called monads, and pretty much almost all of the applicative things we've looked at actually turn out to also be monads, and so they have a sensible way to implement this bind thing. And I'm probably not going to go into that much more, but you can go read about it if you like. It is very interesting, but we just don't have time to do a proper job of talking about that. We probably want to use several classes, but cool. Any questions about this?
For do notation, you still have to have the main equals?
Yes. Yeah, we're defining what main is, and specifically, and actually, let me actually comment out this, and I'll put another main down here, because often the way you would write this is actually, I would often write it like this. That's one way you write it. Basically, whenever it sees the word do, the very next line kind of determines what the indentation will be for that do, and you just have to line everything up underneath there. So this doesn't necessarily have to be further over to the right than the word do. It just has to be further over to the right than like, and you can have nested do blocks and, usually then further away. But basically, it just gives us a nice syntax to define something of type, I/O. Did you want to? Cool. Any other questions? Okay. So let's see if we can actually start turning this more into like a guessing game thing, right? Instead of just doing some silly lookup stuff. So let's see what we do. So actually, yeah, I think before we get there, let's first figure out how to get it to generate a random number. Once we can get it to pick a random number, then we'll turn that. We can just like make it print out the random number, and then we can turn that into a guessing. So we can take out this part about entering a number. Well, I'll leave that. You know what? I'm just going to save this into another file, and then our main we can actually edit. this comment there for now in case we okay, so I want to pick a random number. So let's go look at what was that?
Pseudo-random.
Yeah, it's pseudo-random, exactly. Yeah, indeed. And I think I don't know what I don't remember what what trng uses. I'm just kind of curious. Let's see. I know you can find out somewhere, but anyway. I know there's been some work on that recently. And actually, does it have split? Right. So it actually has this interesting function called split that basically turns one pseudo-random number generator into two in such a way that they're like independent of each other. So like the values that you get from one of the two that you can use won't have anything to do with the values you get from the other one. But it's still deterministic, right? So that's really useful for like if you're doing something, say, with a tree, and you want to like go down and generate random values for the tree, but you don't want to have to generate values for the entire tree. You just want to generate values for the part of the tree that you care about. You can call split, and then like only recurse on the side you care about. But you're guaranteed that it's going to be deterministic. You'll get the same values every time. Not all generators will even support that, but one that's using Haskell support that, which is interesting. All right, let's just do the simplest possible thing. It's actually changed recently. I don't quite. Used to just be like a very simple way to get oh, there, yes, it's just like gives us a simple interface to use it in IO, which there's lots of ways. So this is this is both it's both a great asset of the Haskell community, and also sometimes, or just makes things more difficult sometimes. Is that like people want to get things right? They want to like we're not gonna do a go by halves on this. Like we're gonna use all the latest research and like make it really technically precise, and the types have to make sense and etc. So, you're like, how complicated could it be generating a random number, right? Well, it turns out it's pretty complicated if you really get into the details, and this totally does get into the details. And so, like, this is the module to generate random numbers, and it's like it's super long, right? There's lots of stuff in here, and it's like, so it's both nice that if you're using this in a serious way, like, it'll work, right? You're not going to run into weird, something simpler might work for simple things, and as soon as you start to scale up to bigger applications, it's going to break in funny ways because it's not built for whatever you're doing. This is going to scale, but it's just hard to figure out how to use it at first. So that's the trade-off, right? But yeah, we're going to use something like this. So randomrio says basically you give it a pair of values like a low and a high, and it'll pick a random value in that range. And this M basically can be anything that's monad IO, which essentially we're just going to use IO, like we're going to get an IO in. So like here's an example. We say random RIO, you give it this value, exactly the same output for the same input. Right? It has to be like a function in a mathematical sense. Like, it'd be weird if, you know, in math class, if your teacher was like, okay, we're defining this function from reals to reals, and you put a real number in, it gives you a random real number out. And like every time you call it, it'll give you a different one. You're like, that's not a function. Like, that's a computer program maybe, that's not a function. So you can't have a function in Haskell of type, you know, a comma a to a that gives you a different random a every time. It would have to always give you the same one. So the way kind of around that is, and you're like, well, how is this not violate that? Well, this is going to give us, this takes an a comma a, and it gives us, it doesn't give us an a, it gives us an IOA, which is like, it's like an imperative program. And basically, the program that we get is always the same, right? Just like, you know, if I give you a recipe for a cake, it's always the same recipe for a cake, even though when you follow the instructions, maybe you might get a slightly different cake every time because of, you know, the temperature or humidity that day, or, you know, your flour wasn't quite as good quality, whatever. But the recipe is not changing. And that's the same thing here. Like, the recipe for how to generate a random number is not changing. But every time you execute it, it may give different results. And like, once you're executing stuff in I/O, you lose that guarantee. With like, you don't know what's going to happen, basically. So that's why it has to have a type like this. All right, so we're going to import this. We're going to import system.random. And it's going to yell at us because it's like, I don't know what that module is. So what we have to do, this system.random module comes from the random package. So I have to go in my cabal file, guess.cabal, and I have to go to my builddepends. And basically, this is a big list of all the packages that it depends on. And so I can say random. I could just say random, and then just let it kind of pick whatever version it can find that will work. If I want, and actually it might be a good idea in this case, because I think random version 1.2 is very different than random 1.1. It kind of rewrote a lot of things. So if we write this to work with random 1.2, it may not work with earlier versions. So I might want to specify something like this that says it only works with versions that are greater than or equal to version 1.2. And that's just giving it some information. You know, and I could also, if I wanted to give it like an upper bound, and say, well, you know, only up to 1.3 or something. Yeah.
Caret x one.
The caret thing means, what does that mean? I honestly forget what that means. I think it means something like, it might mean it only works with version 4.16, but not 4.17. Like, it works with 4.16 and anything bigger than that up to, but not including 4.17. That might be what it is. Which is kind of a common thing, because you're like, well, 1.2 is the current version, but when 1.3 comes out, I don't know, it might break stuff. So I might want to specify, I don't know if it's going to work with 1.3. Maybe later, if 1.3 comes out, you could test your program and be like, oh, it does work. So now I can edit this and say, no, it'll work with 1.2 or 1.3. There's actually kind of a big philosophical / social debate on whether you should do that or not. Because some people will say, no, it's really annoying if you put an upper bound, because then if a new version of random comes out, I can't use your package yet because it says it doesn't work. And so like I have to work around that somehow. The other side says, no, it's more annoying the other way, because now if it doesn't work with 1.3, you don't find out, your users find out because they try to use your package, and it says it compiles, but then it breaks. And they're like, I don't know what's going on. So, I don't know. I mean, I would say, like, if you're just making a package and you're just going to throw it out there and you're not going to pay much attention to it, then leave off the upper bound. But if you're like, no, I'm committing to like supporting this and making sure that it stays like, up to date and stuff, then put the upper bound, because then it's not going to randomly break for people. And then you have to do the work of like noticing that. And there's tools that help you notice when things get updated and stuff. But you would then have to go in and like test it and then bump the upper bound. Anyway. So now that I have that in there, it's still yelling at us because I think it hasn't picked up that information yet. But if I build it, it built. And it actually didn't, like, depending on what package we added, it might have to go download the package and build that package. I think I already have the random package installed here, so it didn't have to do that. But I don't know, we could, you know, we could add some other random package just to see what happens. But I might have to like reload this. Yeah, no, I gotta like. Like the editor, my editor kind of like caches information about the project and it starts like, oh, what is it? It's still not good. Oh, fine. No, that's not supposed to happen. I'm not sure why. Something misconfigured, I don't know. Okay, so now we should be able to say something like, you know, and randomrio. Actually, we're going to have the same problem here, I think. The ambiguous problem, right? Because randomrio can return a value of any type as long as it knows how to generate random things of that type. And then print can print anything. So we can again just put like, so what we get to name 30. So every time I run this, it's going to print out a different random number between 1 and 9. Yeah, it's not very random. Yeah. True, yeah. True, it's this weird paradoxical thing. Truly random sequences of numbers often don't look random to humans because like, if humans are like, oh, I want to come up with random numbers, we try to avoid anything that looks like a pattern, because we think that makes it more random. But if it's truly random, you're randomly going to have things that look like patterns. Like, you're going to have something that looks like a pattern, right? Like, any one particular pattern is very unlikely to happen, but it's very likely that you'll have something that looks like a pattern to a human, right? Like everything being in the 40s, or getting 6 3 times in a row, or, you know, whatever. Humans are actually very bad at generating truly random sequences of numbers. So, like, for example, if someone is generating random numbers and you're trying to guess what number they're going to generate next, like, you should probably never guess like the same number they just said, because they're probably much less likely to say the same number they just said, even though, like, they're less likely to say it than it would be if it was truly random. Things like that. There's funny, I mean, this isn't totally tangent, but I don't even know if I can find it now. I've seen, maybe I'll see if I can find it later. There's like a simple, you know, like little interactive web app thing you can find that, where it's just like two areas and you click on one or the other. And basically you can click on whichever side you want and you just keep, you know, click, you know, whatever you want. And then the computer actually is like predicting which one you're going to click next. And then after you click, it tells you if it was right or not. And it's very, very, very hard to get it to hold it to like 50% accuracy, because we're so bad at picking truly random sequences. It can like look at, you know, what you've done up to that point and like make a better than 50-50 prediction of what you're going to do next, just kind of based on what you've done so far. Yeah, it's funny. It's pretty crazy.
I feel like if everyone was like went up to the board or something and you're like had like a 10-digit list of random numbers,
yeah,
then one of us in here would say like, oh, well, there's this pattern.
Yeah,
and then the person would be like, oh,
yeah, exactly.
And they wouldn't even recognize it.
Yeah. Yeah, and if we all did that, like, I mean, maybe now that I've said something, it would change things, right? But if I had just at the beginning of class, like, okay, everyone write down 10 random numbers, and then we like made a graph of them, like, you know, some would maybe be way more likely than others and things like that. Because everyone's like, oh, 7 is super random, so I'm going to put 7, right? It's like, well, 7's not any more random than anything like that. It feels more random somehow. It's like, you know, 5 is right in the middle. That's not random. Anyway, cool. So, got it, picking the right number. So now we're going to say, you know, what are we doing? To an IO action. So what are we gonna do? We're gonna like so probably what do I do? We're just doing this version where we are guessing. Just gonna say so let's try that. Yes. Oh, we should do that each step up. Okay. And then we're gonna say, so we get their guess, and then so first of all, we're going to say, well, actually, because we really, there's like three cases. We're going to see if like their guess is less, equal, or greater than n, and there's actually this compare function. So we can say case compare gn of, and it's either, you know, is less than, it's equal to, or could be greater than. And if their guess is less than the number, we say, let's too low. And then we play game n, because we just want it to continue, right? Haskell doesn't have loops, only recursion. So in Python, this would be a really bad idea. And if my 150 students write a game like this, where they like have a function that just like if they wanted to play again, they just have it call itself, I'm like, no, it's not how we do it. Because Python just isn't built to make that kind of thing, work. Like it'll actually, like the stack will just grow and grow while the function is calling itself. And eventually, if you play enough, it's going to blow up. Also, they're just not thinking, they're not really thinking recursively. They often end up doing weird things where like, you know, it asks if you want to play again, and then you play again, and then because it called itself when you're done, and you say, no, I don't want to play again, it like goes back to the previous one and asks you if you want to play again, and like, things like that happen all the time. But Haskell doesn't have loops. This is exactly the way that we should if we want to play the game again. And Haskell won't have a function stack that keeps growing, because Haskell can see that this is the very last thing that the play game function is going to do in this case, is call itself, and so it just like replaces the stack frame with basically with the new version, and it doesn't have to remember anything about the old version. Yeah.
So that's in a case, do you have to have the arrow thing?
Do you want arrow thing?
The star arrow?
This thing here?
Right, yeah, because just like in the do, you could remove it, but.
Oh, I could remove it if I put a do, so I could say like.
Oh, you do, yeah, okay, since it's a case, you have to add a second one.
Yeah. Yeah, right, exactly. Because the thing, like, in terms of the syntax of Haskell, the thing that's in a case, you have like a pattern and then an arrow and then some expression. It's not like part of a do block anymore at this point, it's just like an expression. And so an expression could be a do block, or it could be something with some operators or whatever, but I'm just gonna put it this way, because like, you know, I mean, do is nice when you have a long thing, but if it's just like, okay, print something and then call play game again, I think it actually looks nicer just to put it on one line, and not, because otherwise you take up like 3 lines having to do it. And I will also mention that for historical reasons, like this operator is a synonym for the star greater than operator. They literally are the same at this point. They didn't used to be quite the same, but I'm just saying if you see some Haskell code and you see that operator, it's the same thing. If it's equal, we'll say you win. And then we will not call play game again, because we're just going to end, right? And then otherwise we're going to too high. Okay, let's try it out. What should I guess? 50. 50. Too high. 25. Too low. Too high. Sweet. Cool. Any questions guess it's 50.
I think that's the 150 thing, isn't it, like 7 guesses?
Yeah, 7. Why?
Do you remember why it's 7?
I think it's why it's half, right?
Yeah, I mean, why is that implied to be 7?
I don't remember why.
Yeah, I mean, right, every time we make a guess, if we guess right in the middle,
Yeah, if you guess 15 and 25,
Right.
then you guess 13 or something.
Right.
We're
having,
yeah,
we're having every time.
You can only do that, so, or you get to 1.
Right. Because, why is it 7 specifically? Well, 2 to the 6th is only 64. If you have something 6 times, you can only distinguish 64 possibilities. If you do it 7 times, 128. And it's actually slightly different than that, because we're not actually literally just dividing it in half every time. We're getting rid of one, we're like doing slightly more than half, because we're like getting rid of the number in the middle plus, yeah. But it still comes out to 7. That it sometimes does require 7, but it is possible to always do it in 7. Or you know, another way you could say that is like the log base 2 of 100 is 6 point something, but you have to round up because you can't do any fractional bit. Yeah.
It's the same reason why, is there any correlation between this, like it takes as much as 7 guesses, is the same reason why you can't fold a paper more than 7 times?
It's related. I mean, it's a little bit arbitrary that those happen to be the same because, like, we just picked 1 to 100 here arbitrarily. And with paper, it's like, well, there's something physical about like how thick paper is and how thick it gets and how much force you need it, you know. But it is related in the fact that like every time you fold a piece of paper, it doubles the thickness, and so like you're dealing with an exponential, like the thickness is growing exponentially. So it doesn't take very many folds before it's so thick that you can't do it. And if you did like 20 folds, it would be like the thickness would be like from here to the moon or something like that. Maybe not 20, maybe like 30 folds. All right. Any other questions about this code so far? I'm just like, what should we do next? I know. How about let's make it so it can play either version, like where we guess or where it guesses. Yeah. So we could say like would you like to guess? I'm going to say like actually we'll say a case just so that they can feel the uppercase letters matter. If they type in Y, then we're going to say
Play game.
yeah, well I don't, so play game you need to give it a number. And I could just say pick a random number and then play game. Just to like decompose things a little more. Let's say we'll call this user guess. So and then otherwise say user guess. Play game is not a very good name because it kind of sounds fair, but computer guess. So first, we're going to prompt the user to, or no, we'll just say, make it take two parameters, which is the like low and high that we're currently working with, right? So low, high. So it's 2 minutes. Actually.
Couple number.
What was that?
You couple one guess number, one guess number.
Oh, okay. And then, all right, we'll say, if there's something else you can do inside of a do block, you can also have let statements where you're just like defining a variable. That's different than the left arrow thing, because the left arrow thing means execute this IO action and get the output of it and put it in this variable. A let, just saying, I'm just defining this variable as this expression. I'm not executing anything. So I want to say like, let's, g equal low plus high divided by 2. This is the middle. And then I'll say put string So I did a $sign here, which just means function application, but it has a very low precedence. So that way, I can also write it like this, with parentheses, because this whole string that I want to print is not just a single string. It's like I'm using this monoid operator to like combine strings together. But since the $sign has very low precedence, it has lower precedence than this operator in particular. So it parses this as, like all this is one thing, and then footster is just applied to that. The $sign just like means we can avoid writing parentheses sometimes. It's not magic, it's just. So then we're going to say so if they typed in L, H, or J, let's see, if they typed in L, then our guess was too low, then we're going to say guess number, what we want to do, our guess was too low, so we now want to go like, our new low is like our guess plus 1, and our high stays the same, right? And if our guess was too high, then we want to keep going with the same low, but our new high is the guess minus 1. And then, or no. Oops. Light string, why did it? Oh, okay, I have to take what? Char, too lower. Would you like to guess? No, yes. The secret number, what should our secret number be? 57. Okay, so 50 is too low, 75 is too high, 62 is too high, 6 is too low, 5 is too high, 7 is too high.
That one sticks.
What was that?
Sticks.
Yeah, 6. Yeah, well, it's definitely going to do the optimal. Cool. So one thing I don't like about this is that like the whole thing has I/O everywhere. So I think one of the things I want to think about next time is we'd like to factor out like so the I/O is there's as little I/O as possible, and then like there's some pure parts of the computation that like doesn't involve I/O. But that may be hard to do with this game in particular, but anyway. So for Friday I'll think of a way that